So we're going to start off chapter 1 with the brief introduction to statistics. So why statistics? The birth of statistics, here's just a brief history. It began in the 17th century, so it happened a while ago. And it was basically a system to find probabilities with inferences. So this way you can determine whether something is true or not based on your own calculations. Statistics is also very important in many different fields, such as psychology, sociology, thermodynamics, which is branched off of physics and chemistry, gambling, which is a risky use of statistics, and computer science, where it is a very prominent aspect of our modern culture. So now that we have covered the history of statistics, here are some important vocabulary. So there's basically two types of statistics. There are descriptive statistics, where you look for patterns, you summarize information, and present them in a form. So this could be like a graph, a normal distribution curve, a chart, a box plot, a histogram, curve, a best line, stuff like that. Inferential statistics is used to make estimates, predictions for the future. So this could be the probability that it will rain the next day in a meteorologist's study. Moving on, there are some important levels of measurements that we must cover or learn more about statistics. The first one is nominal measurement. This type of measurement cannot be ordered or grouped together. So basically you just have a group of items, say a chair, a table, a lamp, a phone, and a calculator. And you just say, okay, we are going to have this, but they do not really have any specific. Ordinal measurements is a measurement or is a set of items that you can group, but you cannot predict what's next. So for example, you can have a set of numbers 1, 7, 221. You can say that they are numbers, and you can order them from lowest to highest, but you cannot predict what's next because of a pattern. An interval level measurement is a predictable pattern, such as 1, 3, 5, 7, and 9. Each of the numbers goes up by a value of 2. A ratio level of measurement is the same thing as an interval measure, but it passes through 0. For example, you have a set of numbers 0, 2, 4, 6, 8, 10. It passes through 0, and you can predict what happens next. Also, different types of studies. The first one is cross-sectional. That's a present study. So if I were to ask any random person, what is your opinion on X survey? They would give me the information, and that is a cross-sectional or present study. A retrospective study is something from the past. So you can ask somebody, oh, what do you think about this thing that happened 5 years ago? They would answer. A prospective type of study is a future study. This is asking or measuring basically something that will happen. Moving on. A population is actually a big thing to study. So what is a population? Population is an isolated group which we want to study. So it's the target study group. Within a population, there are a lot of variables or characteristics of the population. So for example, if you were to take a census, or the population would be the United States of America, and the variable would be that they were Americans. Moving on, another type of population is census, which is measuring everybody in a population. The parameter is a value having to do with the population. So sampling. Sampling is the idea of taking subsets of a population. So instead of measuring the values of 1,000 people, you can take a smaller sample, which you would denote as sample size n, and analyze that, take that as a whole for population. Sampling methods. There are many different sampling methods that we cover. The first one being a simple random sample, which is a sample method where everyone has an equal chance of being selected. So this type of sampling method is totally random. As you can see here, represented by the dots and the x's. The x's have no particular pattern and are basically chosen. A systematic sample is another type of sampling method. It's a pattern used to select. It utilizes a pattern to select different members of the population. So as you can see here, the surveyor took the first person, and they skipped every two to find the next member of the population, or the sample size. The sample of the population. So there's a pattern involved. A stratified sample is a population divided into subgroups, and then a simple random sample is picked from each. So as you can see here, the same amount of dots were divided into separate groups, and a simple random sample was taken each. So a random member of each of the subset. Next, cluster sample. This was a selecting natural groupings. So as you can see here, the samples were grouped together naturally, and one of the natural groups was taken as a representative of the entire population. Next, cluster sampling. Oh, sorry, next, convenient sampling is selecting things at ease. So if a cluster was at the front of the classroom and students are scattered throughout the classroom as teacher, the first four, or whatever the teacher wants to choose. So maybe they're in a row, so it's easier to group them. Moving on. So flaws in statistical thinking. There are basically 8 main flaws that we'll need to watch out for while doing this. First one being biased samples to small sample size, so this is not representative of the entire population. Biased methods of research, which is really common because sometimes they're self-motivated. Before non-response by subjects. A third variable, so maybe not all the variables are controlled. Self-interest studies, which kind of has to do with number 3. Misleading data, so you might present a very bad graph to the person to analyze. They might misunderstand it, present wrong data. Or confounding, where the factors cannot connect. So here are some types of charts that will not be covered, but it's important to know. So dot plots. Dots are on the bottom right, and basically what happens is you take a frequency table, and then you put a dot above each score using the number of frequencies. So the more frequency you have for a specific number, the higher the line. It's kind of like a bar graph. Compared to the histogram, it's different. Next, stem leaf plots. This is another type of interesting graphing technique where you take a set of numbers, and then in the middle of the stem, you put the value on the left hand side of each number. So if you have 2 digits, then the stem number would be 10's value. And on the left and right hand side of the stem plot, you put the a smaller digit. So on a 2-digit number, you have 30, 40, 50. We'll put the second digit on right next to the base stem.
Now we're going to talk about dot plots. Dot plots are a graphical display of data using dots. A dot plot is helpful because a dot plot is a good way to compare, and it's also a good way to show relative sizes. We're going to talk about dot plots by using an example. For example, let's say a classroom of students was asked the question, how long does it take you to eat breakfast in minutes? And these were the following data points. 4 said 0 minutes, 2 said 1, 3 said 2, 1 said 3, 2 said 4, 1 said 5, 0 said 6, 0 said 7, and 2 said 8. And the problem asks us to create a dot plot with the given data. After we get our data points, we need to ask ourselves, where does x go and where does f go? First, we have to make sure we know what f stands for. X stands for the number of minutes it took to eat breakfast. And F stands for how many students said that was their minutes. For example, one person said 3 minutes, while 4 people said 0 minutes, which probably means they didn't eat breakfast. So after we know what X and F are, we can figure out how to plot these points on a dot plot. So to plot these points on a dot plot, we know that X is the number of minutes taken to eat breakfast. So after we know what X is, we can put X on the bottom of the lines. As you can see, the numbers are 0, 1, 2, 3, 4, 5, 6, 7, and 8. So these numbers go on the bottom as shown. And then we need to figure out what to do with F. For each number, we have to put a dot above that X value. For example, for 0 minutes, we need to put 4 dots on top of 0. And for 1 minute, we need to put 2 because that is the frequency. But you don't have to use dots. As you can see, we use stars in our example. But the point is conveyed because we created a dot plot where we plotted the frequencies at which X happens, and then we can use this dot plot to compare. For example, we see that 0 is the most minutes spent on eating breakfast, which means most people did not eat breakfast at all. We can also see relative sizes. Like, we can see the size of 4 and 8 and 1 are the same. And we can see that 2 is greater than 1, 4, and 8, but smaller than 0. A stem and leaf plot is a method of showing the frequency with which certain classes of values occur. The left side of a stem and leaf plot is the stem, and the right side of the stem and leaf plot is the leaf. So these two columns together make up the stem and the leaf, and sometimes there can be more than one leaf, as shown in the previous examples. Stem and leaf plots may be used or preferred to histograms because, unlike histograms, original data points are saved. You can see all of the original data points, but if you make a histogram, these data points will disappear. Next, we're going to show you how to do a stem and leaf plot problem. For the first quiz in algebra class, students received the following grades. The grades they received were 73, 75, 80, 81, 88, 90, 95, 96, and 99. And the problem asked you to create a stem and leaf plot with these data points. So the problem asks you to create a stem and leaf plot with the data points given. The first step to solving this problem is asking yourself what are the stems and what are the leaves. If you're going to create a stem and leaf plot, it's important to know these. After we ask ourselves the questions, what are the stems and what are the leaves, we can begin to solve this problem to create a stem and leaf plot. First, we look at the data points: 73, 75, 80, 81, 88, 90, 95, 96, and 99. These were the grades for the first quiz in an algebra class. So to figure out what the stems are, we look at our data points and we notice that all of the points are either in the 70s, 80s, or 90s. So we can split up their 10 digits into a 7, 8, or 9, and these will be the stems. Then we need to find out what is going to be the value for the leaves. Looking at the numbers 73, 75, 80, 81, 88, 90, 95, 96, and 99, we can find the leaves. For example, look at the number 81. We know 8 is going to be the stem, so for 81, the leaf will be 1. Therefore, we can see that the leaves for our stem 7 is 3 and 5. For our stem, which is 8, we have leaves that are 0, 1, and 8. And lastly, for our stem, which is 9, we have leaves 0, 5, 6, and 9. We now know what our stems are, and we also know what our leaves are for this problem. Then we can finally plot these in a stem and leaf plot and finish the problem. So, as you can see, the left side is the stem, and our stems are 7, 8, and 9. On the right side are the leaves, and so for 7, we can see that we have 2 leaves, 3 and 5. For 8, we have 3, 0, 1, and 8. And for 9, we have 4, 0, 5, 6, and 9. And that is our stem and leaf plot. And we can see that unlike a histogram, which you will learn later on, a stem and leaf plot is helpful when you want to see your original data points. For example, we can go over to stem 9 and see all the data points that fall within that stem. For example, going over to stem 9, we can see that our original data points were 90, 95, 96, and 99. You no longer need your original data table because you have all the data points in your stem and leaf plot.
Now we'll be covering box plots. Box plots contain data like the minimum, the maximum, the mean, the median, which is also known as quartile 2, and quartiles 1 and 2. When you hear the words box plot, do you ask yourself, what's a box plot? A box plot is actually a diagram which helps with the organization of data. Usually on a box plot you'll find the minimum, the lower quartile, which is known as Q1, the median, which is known as Q2, the upper quartile, which is known as Q3, the mean, and the maximum. Here are some ways that a box plot can be organized. In a box plot, you can find the values of the mean and the median within the boundaries of the lower quartile and the upper quartile. This area in between the lower quartile and the upper quartile is called the interquartile range. In a box plot, you can also find the range by finding the maximum and subtracting it by the minimum. When you look at your data and compare the mean and the median, and you find out that they're equal, your graph is going to be symmetric. And when the mean is greater than the median, the graph will be skewed to the right. But when the mean is less than the median, the graph will be skewed to the left. Now we have to test what we learned in a box plot problem. For the first quiz in an algebra class, students received the following grades. Draw a 6-point box plot for the data and determine if the data is either skewed to the right, left, or neither. Since 0 is the lowest score you can find from this set of data, it would be the minimum. And since 10 is the highest score you could find from this set of data, it's the maximum. And to get the mean, you would add up all the x times frequencies with all the frequencies and divide them by each other to get 5. So your mean is 5. And the 13th term on this chart is 3. So your lower quartile is 3. Now we have to find the lower quartile, or Q1. To find the lower quartile, you have to find the 25th percentile of your data. You can do this by multiplying 25% with the number of frequencies that you have, which is 51. And when you multiply 25% with 51, you get 12.75. And you're supposed to round this up to 13. So you're supposed to use the 13th term on the chart as your lower quartile. Now we have to try to find the median, or Q2. The median is pretty much the same thing as quartile 1, but instead of finding the 25th percentile, you're finding the 50th percentile. You can do this by multiplying 50% with the number of frequencies again, which is 51. And when you multiply them together, you'll get 25.5, and that rounds up to 26. So you're supposed to use the 26th term. And according to our data, the 26th term is 5, so our median is going to be 5 also. Now finally, we have to find the last quartile, which is the upper quartile, or Q3. To find the upper quartile, you need to use the 75th percentile. You multiply 75% with 51 to get your term. And you'll get 38.25 multiplying these two values together, but you're supposed to round it up to 39. The 39th term is 7, so your upper quartile is 7. Now we could draw the box plot. On our box plot, we'll have the minimum as 0, the maximum as 10, the lower quartile of 3, a median of 5, an upper quartile of 7, and a mean of 5. Since the mean and the median are equal to each other, the graph is going to be symmetric.
In this section, I'll explain how to attain the minimum, lower quartile, mean, median, upper quartile, and maximum values using a calculator. Using a calculator such as a TI-83 or TI-84 calculator reduces the risk of arithmetic error and reduces the time in creating a box plot and overall increases the accuracy of the calculation. Here are the steps to follow to begin constructing a box plot. First, press your Stats button. 2. Select Edit. 3. Fill in your L1 column. 4. Fill in your L2 column. To the right will show visual aids, which will show you where the buttons are located on your calculator and what your screen should look like. Now that you know how to input data, you can now calculate your values by pressing Stats again. Now, select the Calc tab instead of the Edit tab, then select your Single Variation Stats option. Make sure your L1 and L2 lists are in the proper location. Then, press Enter 3 times to calculate your values. On the right will show a table frequency of college kids drinking relative to certain days of the week. Let's go ahead and try to find the minimum, lower quartile, mean, median, upper quartile, and maximum value using this table. Once calculated, your value should be as listed. Your minimum will be 1. Your lower quartile value will be 4. Your median will be 5. Your upper quartile will be 6. Your max will be 7. And your mean will be 5.08.
Histograms. What is a histogram? A histogram is a common way to visually plot or analyze data. And there are 4 different types of histograms that we learn in this chapter, and these are the frequency histogram, the relative frequency histogram, the cumulative frequency histogram, and the relative cumulative frequency histogram, also known as the RCF. So there are multiple steps to actually drawing the frequency histogram. And the first step is to find the highest and lowest values of a set of numbers. In order to establish a histogram's range, the highest and lowest values of a set must be determined. In this case, the highest value of x is 10 and the lowest value of x is 0. When you're drawing a histogram, you don't want your maximum and minimum points to be on places where you cannot see them. So basically what you would do is subtract a small portion from the minimum value of x and add a bit onto the maximum value of x. So basically for aesthetic means, you have to add and subtract by half of the smallest decimal place from the highest and lowest values respectively. So basically, if your lowest value was 0, you would subtract 0.5, half of the smallest decimal place. And if your minimum value was 0.01, you would subtract by 0.005, half of the smallest decimal place. So in order to find the size of your intervals, you basically take your range and divide it by how many partitions you want. To find the range, you simply subtract the lowest value from the highest value. So in this case, you would subtract 0 from 10. And to find the intervals, divide the range by the number of partitions to find the length of the intervals. And from the starting value, continuously add the length of the interval until you reach the desired endpoint. So for example, in this set of numbers, the number of partitions that you want is 5. And now, before we learned that you should add half the smallest decimal to the maximum and subtract the half of the smallest decimal from the minimum to find your range. So in this case, your range would be 10 plus 0.5 minus 0 minus 0.5, which gives you 11. So the length of your intervals will be 11 divided by 5 partitions, which equals 2.2. And starting from your lowest value, which in this case is negative 0.5 because you subtracted 0.5 from 0, your partition would start at 0.5 and you would add 2.2 until you reach 10.5. So you get negative 0.5, 1.7, 3.9, 6.1, 8.3, and finally 10.5. And these will be the points at where your intervals start and end. So now that you have found your range and your intervals, the next step is to actually graph the histogram. So the most simplistic and easiest histogram that is the most common in use is the frequency histogram, in which you take your x values on the x-axis and you take your frequencies on the y-axis. So for example, this first range is negative 0.5 to 1.7, and these x values would include 0 and 1 from the set of numbers. Now, you have 0 and 1, so you would take the frequencies of both these numbers and add them together and put them on your y-axis. And you would do the same for all the antecedent categories. 1.7 to 3.9 would include 2 and 3. 3.9 to 6.1 would include 4, 5, and 6. 6.1 to 8.3 would include 7 and 8. And 8.3 to 10.5 would include 9 to 10. And you just add up the frequencies in this range and you just put them on the y-axis. So the next graph is called a cumulative frequency histogram. A cumulative frequency histogram is practically the same thing as a frequency histogram. However, you would add up the frequencies until the end of the interval. So for example, the first interval is negative 0.5 to 1.7, and as we said before, these include the numbers 0 and 1, so the frequency would be 3 plus 1, which is 4. However, when you move on to 1.7 to 3.9, you would add up the number from the preceding category, which is 4. You would add that to the next category, which is 2 and 3. So when x equals 2 and x equals 3, you get the frequency equals 5 and 6, which equals 11. So you would add 11 to the preceding category, which is 4, and you would get 15. And now you do that for all of the next categories until you finally reached your endpoint, which should be equal to your total. And in this case, the total is 51. This next histogram is called a relative frequency histogram. A relative frequency histogram uses the same information as a frequency histogram, but instead it compares each class interval to the total number of items. For example, the first interval from negative 0.5 to 1.7 is equal to 4, and it contains 4 out of the total 51 items. So the relative frequency of the first class interval is 4 over 51, which equals 0.784. And if you multiply that by 100, you get 7.84%. And if you do that for all the other intervals, then you would get a certain percentage of the total frequency. The only difference between a frequency histogram and a relative frequency histogram is that the vertical axis uses relative or proportional frequency instead of simple frequency. The last type of graph we learned in this chapter is called the cumulative relative frequency graph. The cumulative relative frequency graph is practically the same thing as a relative frequency graph. However, it uses percentages rather than frequencies. The cumulative relative frequency graph is the accumulation of previous relative frequencies. So basically, as you can see in this graph, from negative 0.5 to 1.7, you have 4 divided by 51, which gives you 7.84%. From 1.7 to 3.9, you would get 11 divided by 51, which would give you 21.57%. Now what you do is you add 21.57 to the preceding interval, 7.84, and that gives you 29.41%. And basically you just do this and keep on adding the amounts from every interval until you reach the final point for 100%.
Next, we're going to learn about sample variance. For n amount of measurements, the sample variance is sum of the squared distances from the mean divided by n minus 1. To find the sample variance, the first step is to find the mean, or x bar. Then the next step is to subtract the mean from each distinct n, and then square the difference. The next step is to multiply the numbers by the frequency in which they appear. The next step is to add the resulting numbers and then to divide by n minus 1. We divide by n minus 1 but not n. This is because we are finding the sample variance, and an important property of sample statistics is that it helps you estimate the population parameter. If you evaluate the sample statistics for every possible sample and find the average, then the average of the sample statistics should equal the population parameters. For example, if we're trying to find the mean of a certain population, we should be able to take the means from every sample, every possible sample, and when we find the averages between those samples, then it should give us the population mean. So when we divide by n minus 1 in the sample variance, it becomes an unbiased estimator of the population variance. As you can see, for populations, you divide by n, but for what we're doing, sample variance, you divide by n minus 1. This is a sample variance problem. You are considering adding a new stock that has an expected return of 4%. Before you buy this stock, you would like to know its variance. Using historical data, calculate the variance of the stock's returns. The data for the stock's returns are shown on the left, and the first step is to find the mean. To find the mean, we take each x and we multiply it by the frequency. And so when you add up all the x times f's and you divide it by the total number n, which is f, then you get 0.48 divided by 12, which is 0.04 for the mean. The next step is to subtract the mean from each distinct x and square the difference. So we take each x value and we subtract the mean from it, which is 0.04. And after we find the difference, we square each number. We then take each squared number and multiply it by the frequency. As you can see, we multiply each of them by 1 except for two numbers, because these two numbers had x values that appeared 2 times on the chart. We then take the final number, which is x minus the mean squared times f, and we add up all the numbers, and we get a sum of 0.0026. The last step to find the sample variance is to divide by n minus 1. And because n equals 12, we divide by 11. And then we get the answer to be 0.000236, which is the sample variance. Now we are going to talk about the sample standard deviation, which is a measure of the dispersion and a distribution. The equation to find the standard deviation is to take the positive square root of the sample variance. The steps to find the sample standard deviation is to find the sample variance and then to take the positive square root of it. The sample standard deviation problem is you're considering adding a new stock that has an expected return of 4%. Before you buy this stock, you would like to know its variance. Using historical data, calculate the standard deviation of the stock's returns. This is the same problem as the sample variance problem that we did earlier, except instead of knowing the sample variance, we are now calculating the sample standard deviation. From the last problem, we found that the variance was 0.000236. So to find the sample standard deviation, we just have to take the square root of that. And the square root of 0.000236 is 0.01536, which is the standard deviation. Now we are going to talk about the coefficient of variance, which is the ratio of the standard deviation to the mean. We find the coefficient of variance because it's another way to describe variation, and it describes the dispersion as a percentage of the mean. Generally, having a coefficient of variance that's less than 5% means good performance. The formula is standard deviation over the mean times 100%. Here's a coefficient of variance problem. Data from experiments show a standard deviation of 4.00 milliliters at a concentration of 100 milliliters, and a standard deviation of 8 milliliters at a concentration of 200 milliliters. What are the coefficients of variance? So to find the CV, we have to take the standard deviation over the mean. And so we take 4 divided by 100, and we also take 8 divided by 200. And this gives us 4%. So the coefficient of variance for both is 4%.